Specifically, it was about, I guess, the terminology involved in talking about terminal arms and angles associated with those terminal arms. Just to run through all of these things, I don't have it typed up and I'm not going to write it out. An angle in standard position is also called a rotation angle, and it is the number of degrees that you rotate counterclockwise from the positive x-axis to get to what's called the terminal arm. Contrasting that, however, with what's called a reference angle, and you might wonder why we're even talking about a reference angle, because if I just tell you the reference angle, it doesn't really tell you much. It doesn't tell you where the rotation angle ends. It just tells you what the reference angle is. But we'll learn about the importance of it later. What the reference angle is the angle, the smallest angle, between the terminal arm and the x-axis, wherever that is. Maybe it's so many degrees above the positive x-axis or below the positive x-axis or above the negative x-axis or below the negative x-axis. One of the things is not absolutely crucial, but I think it's helpful in understanding later on the importance of these things, is that when you talk about a rotation angle, it has a direction to it. It's hard to see, but all of these diagrams, those red arcs, this is question 2 of your textbook, those red arcs are pointing in a direction. They're pointing from the initial arm, which is the positive x-axis, to the terminal arm. But a reference angle doesn't have any direction associated with it. So and I don't care what this question is asking, that's not my point right now. In this diagram here in the bottom right corner that's labeled F, if I were to label the reference angle, that's this angle here, theta reference, and there's no direction associated with it. Okay, it's just an angle. I think that pretty much covers it. Let me get back to where we were here. So can you take a look at your work, please? The practice problems. Does anybody have any questions you would like me to go over? Go ahead.
Question
6? So determine the measures of the 3 other angles in standard position that are between 0 degrees and 360 degrees that have a reference angle of, and we need to pick one. Okay. I don't really like the way this is worded. Okay. I would rather it says that. I mean, there's something implied here, and what's implied is that if we pick on C, for example, what's implied is that that 30 degrees is a rotation angle in quadrant 1. And it's saying if that's 30 degrees in quadrant 1, the reference angle is 30 degrees, then you know the rotation angle is also 30 degrees, right? What this question is trying to say is all of that, period, what are the other 3 rotation angles? Does that make sense so far? Okay, so what it's saying is, if you have a reference angle of 30 degrees in quadrant 2 and in quadrant 3 and in quadrant 4, what are the rotation angles? So I'm going to sketch those 3 situations. I'm going to get rid of this. And again, I know I can be repetitive, but sometimes words don't really, they just go right through you. What this is saying is, in quadrant 1, the reference angle is the same as the rotation angle. If the reference angle is 30 degrees, for the other 3 cases, what's the rotation angle? So we would sketch a 30-degree reference angle in quadrant 2, in quadrant 3, and in quadrant 4. This is our 30 degrees, the reference. This is our 30 degrees, the reference angle. This is our 30 degrees, the reference angle. The rotation angle is that, which is what we're asked to find. Is this, is what we're asked to find. And this, which is what we're asked to find. And I think you could probably finish it, but I will finish it anyway. In the case of the one that I'm standing closest to, the one on the right, I would have to take 360 degrees, which is a full revolution, and back off that 30 degrees, giving me 330 degrees. Over here, I would need to take 180, which is this black arc, and add the reference angle of 30, giving me 210 degrees. And I was a little sloppy with some addition yesterday, so correct me if I'm getting any of these wrong. Over here, we would have to take this, which is 180 degrees, and we would have to back off that reference angle of 30 to get 150 degrees. Is that okay, Ali? Okay. You don't need me to do any of the others on this one? Okay. Any other questions? That's the objective, to find the three primary trigonometric ratios of the special angles in quadrant 1. So I want us to make a note here of what I mean by a special angle. A special angle is an angle that's a multiple of 0 degrees, 30 degrees, 60 degrees, or 45 degrees. Now, I realize I'm being unnecessarily repetitive here, because if I say a special angle is any angle that's a multiple of 30 degrees, then I don't need to include 60 in my list, because 60 is already a multiple of 30. But I want you to get used to seeing, and in fact, you know what? I'm going to add 90 as well. I want you to get used to seeing those particular angles as being what we consider to be special. They're special because in trigonometry they become very useful for a lot of problems. If I were to take a look at these angles in terms of locations, and you do not need to draw this. If I had a circle on the coordinate grid, so this is building up to something that you're going to see a lot of in 30-1. If I looked at multiples of 90 degrees, well, that would be this location. That's no 90s. This is 190. This is 2 90s. This is 3 90s. And then we're back over here to 4. If I were to look at multiples of 45 degrees, that would be here. That's 45 degrees. Another 45 takes us to 90. Another 45 takes us there. Another 45 takes us here. And we continue in this fashion. These are all special locations. If I were to look at multiples of 30 degrees, 30, 60, 90, another 30, another 30, another 30, another 30, another 30, another 30 here and here and here and here. This is what we mean when we talk about special angles. So if you look carefully at the objective, it says special angles that are in quadrant 1. Well, what are those? That would be 30, 45, and 60. And then also we're going to be looking at 0 and 90. So what does this mean? What does this objective mean? It means you should be able to, at the end of this lesson, this is the goal, tell me what the sine of 45 degrees is without using a calculator. You should be able to figure out what the tangent of 60 degrees is without using a calculator. That's what we mean by the three primary trigonometric ratios. So I'm going to add one more thing here, that this means sine of the rotation angle, cosine of the rotation angle, and tangent of the rotation angle. You should be able to tell me the exact value without using a calculator of the sine of 0 degrees, the cosine of 0 degrees, the tangent of 0 degrees. The sine of 30 degrees, the cosine of 30 degrees, the tangent of 30 degrees, etc., 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 without a calculator. Okay? And you're going to discover there are ways to cheat, but the ways that you might discover to cheat to get these numbers without using your calculator are not useful by the time you get to 30. So you will hear me say this often in this course. There might be simpler ways to get answers in this course, but if all you know how to do is the simple method, you're going to fall flat in the next course. Okay? So, you're given a task here. There's a triangle. This is a right triangle, and the two acute angles are 45 degrees each. The acute angles in a right triangle are always the angles that are less than 90 degrees. The question is, if the hypotenuse of that triangle is 1, how long are each of the other two sides? Well, first of all, I hope you recognize that the other two sides are equal in length. They're equal in length because if those two angles are each 45, then this is what you call an isosceles triangle, which means the two sides other than the hypotenuse are equal. So these two sides are the same. Let's call each of the two sides L. I do not want to use X here for a reason that might become apparent later. Well, this is really a Math 9 problem now, or a Math 8 problem. We can use the Pythagorean Theorem. Now, before I actually write out the Pythagorean Theorem for this triangle, how many of you recall being taught that the Pythagorean Theorem is something like a squared plus b squared equals c squared? Or a squared equals b squared plus c squared? I've always hated that. The Pythagorean Theorem is this. You're not going to be so fortunate to have a triangle labeled A, B, and C where the hypotenuse is C, because sometimes the hypotenuse will be A and sometimes it will be R. This is a deeper meaning in mathematics. The Pythagorean Theorem is not a formula, it's a relationship. The relationship is that when you square the hypotenuse and then you square the other two sides, the sums of those other squares add up to give the square of the hypotenuse. So in this particular case, you're going to have L squared plus L squared equals the hypotenuse squared. Well, the hypotenuse is 1. Right? This is the hypotenuse. The hypotenuse of a right triangle is always the longest side. Once again, you didn't have to choose L. You could have chosen any variable you wanted to. L squared plus L squared is 2L squared. This is 1L squared plus 1L squared. You know, 1 kitten plus 1 kitten is 2 kittens. 1 pesos plus 1 pesos is 2 pesos. 1L squared plus 1L squared is 2L squared. On the other side, we have 1 squared. Well, 1 squared is 1. So I'm going to divide both sides of this little equation by 2. And I'm left with now this statement that says L squared equals 1/2. And that means I can take the square root of both sides. The square root of something squared just gives you that thing. Let's just talk about this. Take your calculator. Take 11.58 and square it. And now take the square root of that. It's like a really cheesy magic trick. You get 11.58, don't you? Because squaring and square rooting are opposite operations. By the way, you could take 11.58 and square root it first and then square it, and you'll still get 11.58. A little bit off topic. Anyway, That means that on the left side we get L. Now today we are all about exact values. So I want to just pull off the road for a second and just forget about this question. And I want to ask you a question. Can somebody tell me what this is equal to? Will? No. And don't feel bad because you're not getting the right answer. I don't expect anybody to get the right answer because you haven't really been taught this. I don't want to say, well, you haven't really been taught this in grade 10. This is not equal to 1.4. It's not. And I could ask you to change your answer and you might say 1.41, right? Or 1.414. The point is, from grade 10, this is an irrational number. And again, I have never had anybody give me the right answer to this question. I'll tell you what the right answer is in a second. An irrational number is a number whose decimals, when you look at it in decimal form, go on forever with no repetition. It cannot be expressed in decimal form, and it cannot be expressed in fractional form as an exact value. And as I said, we're looking today at exact values. So, does anybody, I know I haven't instilled a lot of confidence in you by saying that, right? I've set you up for failure. But does anybody know what this is equal to? It's equal to root 2. That's what it is. You cannot write the square root of 2 or say what the square root of 2 is in any other way. You're exactly right. It's equal to root 2. So when you say, what is this equal to? You have to say, well, it's equal to root 2. You cannot write it any other way. Which is a really weird thing. You're used to wanting to put a number to something, right? Like 1.4 or 1.41 or 1.414. I don't remember what the other decimals are, but we can't do that because we want exact values. And we're kind of in the big time here. This isn't junior high where we can go, oh, it's 1.4. That's close enough. So now getting back to the question, you learned last year, and we will talk a little bit more about it this year, but you have learned in the past that when you have the square root of a fraction, you are allowed to take the square root of the numerator over the square root of the denominator. So I want to demonstrate this fact to you, so we're going to pull off the road again. And one of the reasons I really like this course is when we learn stuff, it's not in isolation. It's connected to everything else. That's why we have to take these little detours from time to time. What is the square root on your calculator in decimal form? So now I'm going to say, let's look at the decimals of 3/5. Now we know that the number that your calculator is going to pop out is not exactly the square root of 3/5 because it's a irrational number. But if I take the square root of 3 divided by 5, notice that the square root forces me to put an opening bracket there where I go 3 over 5 and I close the bracket. I get this decimal. Now, what if you take the square root of 3 divided by the square root of 5? Well, the square root of 3, we have to close that brackets. We have to close that set of brackets divided by the square root of 5. You get the same number. Now, look, we know that it's an irrational number, so those decimals go on forever. But you know I'm not trying to fool you here, right? The decimals are going to be the same all the way to infinity. My point is, just with that little exercise, that we are allowed to write the square root of 1 over the square root of 2 instead of the square root of a half. Now, can I figure out what the square root of 1 is? Yeah, it's 1. So the square root of 1, the numerator of this, is just 1, and the square root of 2 is the square root of 2. What's the difference between the numerator and denominator? The numerator was the square root of a perfect square. So I can take the square root of 1. So what we have learned is that the exact value of the other two sides, if the hypotenuse is 1 over root 2. Now, everything is kind of coming to a head here in high school math for you, and there's all these things coming in from different angles. And as I said, it's not nice and linear. We got to just pull off again for a second, because I want you to use your calculator and figure out the decimal value, the approximate decimal value of 1 divided by the square root of 2. And you should get approximately 0.707. Am I right? You see that little dot I put over the equal sign? That means approximately. It means it's not equal to that. It's approximately equal to it. What I would like you to do now is figure out what this is equal to approximately on your calculator. Now you're going to have to close the brackets on the 2 that you're taking the square root of before you divide by 2. But what you will discover, I'll show it up here. So for the one on the left, I would go square root of 1 over 2 and close the brackets. For the one on the right, I would go the square root of 2, close the brackets, divided by 2. It's the same number. So what? Well, from here on in, if you say 1 over root 2 and the person beside you says root 2 over 2, you're both right. If you get 1 over root 2 on an exam and the multiple choices don't have that, but they have root 2 over 2 instead, then go with that. You need to know those are the same numbers. And by the way, that extends to any number. I don't want to explain why it works that way, but it's true. You could try it with any number and it's going to be the case. So, we've answered the first question. And I will tell you right now that this triangle along... Oh, that was a mistake. My computer's locked up. This triangle along with... We'll have to wait for it. Those lengths, there it is, are things you need to know. Okay, so you have two options here. Don't worry about why you need to know them. You need to know them. You could memorize that triangle, or you could draw it and put 1 on the hypotenuse and do what we did on the left to determine the lengths of the other two sides. But I would suspect that after a little bit of work, you will know with this triangle, the two short sides are 1 over root 2 or root 2 over 2. Okay, let's move on. There's one. Notice, by the way, this triangle contains a special angle, doesn't it? 45 degrees. Let's figure out now, with the second part of this kind of warm-up, if I have this triangle with the hypotenuse equals 2, and you'll learn why having the hypotenuse as 2 is a good choice. What are the lengths of the other two sides? I want you to notice that we have two special angles. There's the 30-degree angle, and there's the 60-degree angle. Well, I'm going to just throw it out here and tell you that the length of this side will be 1. And I'm wondering if anybody knows why the length of that side is going to be 1. Once I explain it to you, it'll be hard not to know. Yeah.
Hypotenuse is 2, so half of the, and 60 degrees is one of the angles for equilateral triangles.
Yes, yes. Let's pause for a second and let everybody take that in. This is not an equilateral triangle, but you're talking about an equilateral triangle, okay, where you have 60, 60, 60. Go on.
Then if the right angle connected to the other half of the hypotenuse, then that would be a right or an equilateral triangle, and half of 2 is 1, then that would
Okay. And I suspect you know exactly what's going on in your head. I'm going to add a little something to it. I understand what you're saying because I know the answer. If we take, let me take this triangle. Oh, let's do it this way. I'm going to take this triangle. And I'm going to flip it upside down. And I'm going to draw it here. Is this kind of what you had in mind? You were thinking of it in a different way. Okay, well, we could talk later. I'm sure your way makes sense as well. All I've done is I've taken that triangle and I've reflected it. Now, if you focus on the big triangle I've created, if this was 60 degrees up here, then this is 60 degrees here. And if this was 30 degrees, this is 30 degrees, which makes this 60 degrees. So this whole triangle has 3 angles that are equal, which means that triangle is equilateral. And by the way, however you're sorting it out in your head, if it's a different way and it works, it doesn't matter. We want the answers here. So if this is equilateral, then that means that this length, and this length are all equal. And that means that this vertical length is 2, and the only way that's going to happen is to have 1 and 1. So now what's important? What is important is when you take a look at this triangle, the shortest side, if it's a 30 degree, 60 degree, 90 degree triangle, the shortest side will always be half of the hypotenuse. Always. So I'm going to erase this and say that this is our starting point with this triangle. How do you know that's 1? Well, I know it's 1 because if I fold that triangle over, I get an equilateral, which means that short side has to be half of the hypotenuse. Are you with me? Okay. How can we find the missing side? Let's call this, let's call it M for no particular reason. I just want to avoid X. I want to avoid Y. Well, we can use the Pythagorean Theorem. And the Pythagorean Theorem will say m squared plus 1 squared is equal to 2 squared. So when I square 1, I get 1. When I square 2, I get 4. I can subtract 1 from both sides and get m squared is equal to 3, which means m is equal to the square root of 3. So what is the square root of 3? The square root of 3. What is the square root of 3 approximately? It's approximately, and this is where you can use your calculator, I believe it's approximately 1.73. Yes? Okay. But we don't want to write 1.73. We want to write root 3. It's useful to know about what it's equal to, but we don't want to do that on paper. We just want to leave it as root 3. So what am I telling you? The risk of locking up my computer again. You need to know intimately this triangle. You need to know that with this triangle, when the hypotenuse is 2, the shortest side is 1, and the other side is root 3. How do you know that? You could memorize it, or you could build it whenever you need to use it. And my first reaction to this when I was taught it way back when is, this seems as though somebody has just invented a bunch of math to make my life difficult. It really does seem that way. But it has real uses. There really is not much you learn in high school math that you don't use moving forward. Nothing, really. So you need to know these two triangles. Do you see what I've done with the triangle on the right compared to what we wrote down? I've written root 2 over 2. So why do we need to know these triangles? If I go full circle now to the beginning of the lesson, I said, let me show it to you. That all of these angles, you need to be able to tell me the sine of, the cosine of, the tangent of. Without a calculator. So, if I asked you what is the cosine of 30 degrees, well, I know what the cosine of 30 degrees is. It's root 3 over 2. And why do I know that? Because when I look at a right triangle that has a 30-degree angle in it, and I know that cosine of an angle is the adjacent side over the hypotenuse, the adjacent side is root 3 and the hypotenuse is 2. I know the cosine of 30 degrees is root 3 over 2. Do me a favor on your calculator, and we will formalize this in the notes in a second. Calculate what the square root of 3 divided by 2 is in an approximate decimal form. 0.866. Yes? And by the way, it might be helpful for you to, after you see that a few times, go, oh, 0.866, that's the root 3 over 2. It's a little way to cheat. Now go ahead and take your calculator, make sure it's in degree mode, and take the cosine of 30 degrees. It's the same number, right? Now you may not be very impressed, but that's a pretty powerful set of skills to be able to find the cosine of 30 degrees without a calculator. So what we're going to do is complete this chart. What is the sine of 30 degrees? I'm going to remind everybody, first of all. Oh, look at that. You see what I've done with the triangle on the left? I've flipped back to 1 over root 2. You can go root 2 over 2 or 1 over root 2. I will remind everybody that sine of an angle is opposite over hypotenuse from grade 10, and cosine of an angle is adjacent over hypotenuse. Remember last year you were given those on your formula sheet? You're not given them this year. Okay, you have to know them. So what is sine of 30 degrees? Okay, if we're going to look at sine of 30 degrees, if we're going to look at sine of 30 degrees, then we're going to have to focus on the 30-degree angle. And the sine of 30 degrees is the opposite. Well, this is opposite to the 30 degrees, and this is the hypotenuse. So the sine of 30 degrees is opposite over hypotenuse, which is 1 over 2. By the way, all that's saying is the shortest side in a 30-degree triangle is half of the hypotenuse. Let's do now cosine. No, let's do cosine of 60 degrees. So I'm done with looking at the 30 degrees. Let's do cosine of 60. So we're going to have to look at the 60-degree angle. We're also looking at cosine, which means we're talking about adjacent over hypotenuse. What's the adjacent side to the 60 degrees? Well, it's 1. This is the adjacent side. And this is the hypotenuse. So cosine of 60 is 1 over 2. Before I talk about the deeper meaning of what I'm trying to get across to you here, can you take your calculator and take the sine of 30 degrees on your calculator? You get 0.5, don't you? because the sine of 30 degrees is 1/2. So what does this mean? It means that if you make a triangle with a 30-degree angle in it, and your triangle is really small or really big, the opposite to the hypotenuse will be 1/2. Go ahead and take the cosine of 60. Get 0.5. Does anybody want to give me a reason why the sine of 30 and the cos of 60 are the same? Why is the sine of 30 going to give you the same as the cos of 60?
Because they're referring to the same side. Or would it not really matter for this?
Well, they're referring to the same side because when you talk about the cosine of 60, the adjacent side is the opposite side when you talk about the sine of 30. What is it about those two angles that ensures that's going to be true?
They're complementary.
Yes. Wow. I can't believe you pulled that word right out of the air like that. I always have to think about that. They're complementary, which means they add up to 90. We won't worry about supplementary versus complementary, but they add up to 90. So we're just kind of in a playing mode here. Take the sine of 10 degrees on your calculator and take the cosine of 80 degrees because 80 and 10 are complementary. You get the same number, don't you? Okay. What about the cosine of 30 degrees? Well, this time we're going to focus on the 30-degree angle, which is right here. And I'm looking at cosine. I'm going to stop with the highlighting. Cosine is adjacent over hypotenuse. So if I take a look at the 30-degree angle, adjacent is root 3, hypotenuse is 2. So the cosine of 30 is root 3 over 2. Can you confirm that? Like take root 3 over 2 on your calculator, see what you get, and then take the cosine of 30. I'm asking you to do this because I want you to start recognizing that root 3 over 2 is that 0.866 number, which is a way of kind of cheating. Like really, everybody, if I'm telling you, think about this. I'm telling you, by hook or by crook, I don't care how you do it, you need to know this. Couldn't you just go cos of 30 on your calculator and go, oh yeah, that's root 3 over 2. You know, if you can remember that, it's helpful. What is sine of 60? Well, we go over to the 60-degree angle. Sine is opposite over hypotenuse. Well, opposite's root 3. We're going to get root 3 over 2. What is sine of 45? Well, now we're looking at this 45-degree angle. Sine is opposite over hypotenuse, although do you see that it really doesn't matter whether we look at opposite or adjacent? In other words, we're going to get opposite, which is 1 over root 2, over 1. Well, when you divide by 1, you're just left with the same thing. And when you do it for cosine, you're going to get 1 over root 2. Now, I'm make no mistake about it. This is important in Math 20-1 solely because it becomes important in 30-1. Okay? If I asked you for the decimal value of 1 over 2, I hope everybody knows it's 0.5. How many of you know, without using your calculator, the approximate decimal value of root 3 over 2? Yeah, but don't keep it to yourself next time. I'm asking people to think. 0.866. Well, since we've become familiar with this decimal value, why don't we become familiar with 1 over root 2 or root 2 over 2? Does anybody remember what it was? Okay, check it out on your calculator just to make sure. I think it's the 0.707. So literally what I'm saying is you need to know these 6 things. There's more to it, but you need to know these 6 things. So if you're ever asked what is the sine of 45 degrees and you don't remember, use your calculator, go sine of 45, see that it's 0.707 and go, oh yeah, no, that's that root 2 over 2 or 1 over root 2. Any questions with that chart? All right. Well, I can't really explain why these numbers are going to come out to be what they're going to come out to be because we can't construct triangles where we have adjacent and hypotenuse relative to 0 or 90 degrees. It doesn't work. But use your calculator, find the sine of 0 degrees, the cos of 0 degrees, the sine of 90, and the cos of 90, and fill it in. Correct? I will maybe explain to you why they have those values later, but it is not important right now. If you're ever asked for the sine of 90 degrees, then use your calculator. Okay. I do want you to notice, though, that the cosine of 0 and the sine of 90 are the same because 90 plus 0, those are 2 complementary angles. Okay, now we're going to do some examples. Some of the examples are related to that, others are not. This first set of examples, number 1, is all about an extension of yesterday's work. If we have an angle in standard position of 65 degrees and we reflect it in the y-axis, what's the new angle of rotation? The way that you're going to solve this is you're going to sketch it. 65 degrees is here. I may have drawn that a little big, but that's okay. If I reflect it across the y-axis, that means that I'm treating this as like a mirror. And just like if I stand in front of a mirror, I see behind the mirror a reflection of that. I'm going to get a reflection behind the y-axis, and it will be here. And what the question is what is this rotation angle? Well, you can figure that out. Because if it's reflected, this has to be 65 degrees as well. Right? If I look at a reflection of my hands across the y-axis, it isn't that I reflect this hand across the y-axis and I get that. I get symmetry. So if that's 65 degrees, then this rotation angle all the way to that point, this rotation angle is going to be 180 minus 65 degrees. There's nothing particularly illuminating about this example. It's just an application of rotation angles and reference angles. Is that 115? Is my subtraction correct? Okay, good. So this would be 115 degrees. Well, I would like you now to repeat the process. If this is 65 degrees and I reflect it across the x-axis, I would like you to figure out what the rotation angle will be. How many of you basically know what to do in your head? You're looking at it, and it would be 360 minus 65, wouldn't it? Because if I reflect it vertically, I'll use black for the vertical reflection. It's going to be there with this being 65 degrees. So the rotation angle will be from here all the way around, which is 360 minus 65, which is, help me out here, 295? Okay, good. And now we get into the problems related to what we've just spent. Oh, there's one more, isn't there? Reflected in both axes. You do have a part C, don't you? Okay. So if I reflect it in both axes, it's here. When I reflect it in the x-axis, it goes here. When I reflect that in the y-axis, it goes here. You know, I think the bigger point of this is anytime you reflect one of those arms, the reference angle stays the same. It's always going to be 65 degrees away from the x-axis. What we're asked to determine is this rotation angle. So looking at our diagram, theta would be 180 plus 65, which is 245 degrees. Yes? Okay, good. All right. So now the remainder of the examples are things that you could have done last year in grade 10. They're grade 10 questions with a little twist. So let's take a look at the first question. The pendulum of an arm of a metronome is just something that you use in music to keep time. It's like a pendulum on a spring that goes back and forth regularly. The length of the arm is 10 centimeters, and it's moving back and forth from a position of 30 degrees as a rotation angle to 150 degrees. So let's sketch that. We're going to have to sketch this over top of a coordinate grid because it talks about rotation angles. It starts at 30 degrees. So this angle in here is 30 degrees. And it ends at 150 degrees. I really hope that you understand the significance of it ending at 150. That also is 30 degrees away from the x-axis. And what that means, if this is 30 as well, because 150, and you can really make a mistake of making your diagram too cluttered, but 150 degrees is this. What this means is if you connect the two endpoints, you'll get a horizontal line. Because that length of 10 is 10 on both arms, and if both arms are 10 and both arms are 30 degrees above the x-axis, both arms rise the same amount. What horizontal distance does the tip move in one beat? So what we're asked to find is how far horizontally the tip moves. We want to find that highlighted length. And this is what I mean by saying this is a Math 10 problem. Because all we have here is a triangle. Here's the triangle, and I'm going to peel away all of the unimportant information. Here's the triangle. And you're trying to find that, right? So how can we do that? Well, if this is 30 degrees and this is 30 degrees, this can be figured out because we know that all three of those angles have to add to give 180. That's got to be 120 degrees. But we like to work with right triangles, so this is the best thing to do. So we've taken the words and turned it into a geometry problem. And in my mind, the thing that I would want to do here is use one of these triangles to find L. Use one of these triangles to find L, and then worry about finding X by doubling it because the two triangles are identical. We're going to do this without a calculator. Okay? So last year, when you look at a triangle that's a right triangle, with a missing side, you pick an angle. We're going to pick the 60 degrees. We identify the side that we want to find as being opposite, adjacent, or hypotenuse. So in relation to the 60 degrees, do you agree L is opposite? Okay. So if we use 60 degrees for theta, L is the opposite, and the hypotenuse is 10. So in grade 10, what you would do is you would use sine of theta equals opposite over hypotenuse. So you would have this. Sine of 60 degrees equals opposite, which is L, over the hypotenuse, which is 10. Correct? Nothing complicated here. Don't be scared of this. There's nothing confusing. This should be fairly basic. And then what you would do, or what I would do, and you all had different Math 10 teachers, is I would basically cross multiply and say that L is equal to 10 sine 60. Would you agree? And then what you would do is you'd grab your calculator and go 10 sine 60. But I'm saying we don't want to use a calculator. You should know what the sine of 60 is. This L is going to be 10 times whatever the sine of 60 is. And we know what that is by looking at a 30, 60, 90 degree triangle. On this triangle, we label the hypotenuse as 2. We remember that the shortest side is 1. And hopefully you remember the side across from the 60 is root 3. The bottom line is, looking at this triangle, sine of 60 is opposite over hypotenuse. It's root 3 over 2. So that length is root 3 over 2 times 10. We can simplify that because 10 divided by 2 is 5. So that length, L, is 5 root 3. Now, just to convince yourself of it, on your calculator, take 10 sine 60. On your calculator, take 5 times the square root of 3. You'll get the same number. This is what's different. You have to be able to put the number in here for the trigonometric ratio without using your calculator. Are there ways to cheat and weasel and maneuver your way around that rule? Sure. But if all you do is that, then you'll miss out in the end. Anyway, that's not the answer, is it? What do we have to do to that to get the answer? Yeah, multiply by 2, because that was only L. So this is 5 root 3. Plus 5 root 3, which is 10 root 3. You haven't actually been taught this before, but officially, but 5 root 3 plus 5 root 3 is no different than 5 puppies plus 5 puppies. You have 10 puppies. 5 root 3 plus 5 root 3 is 10 root 3. So the answer to this question is x equals 10 root 3. And to be honest with you well, I'm always honest with you, but to let you in on a little secret, in every course there's just a couple of lessons I dread teaching. And this is one of them, because I know in a few minutes when you're going to try this on your own, how much you're going to struggle. Okay? And I think it's just the nature of this. I wish I could snap my fingers and come up with the perfect way to explain it so everybody understands it. But I can't. So the point is, when you are on your own and you're struggling, that's normal. This is not something that everybody gets automatically. Let's try one more. The tempo is adjusted, so it swings from 45 to 135. So what's happening here now, and by the way, if you get it, that's great, but not everybody will initially. What's happening here is it's going from 45 on one side to 45 on the other, because this is what we learned yesterday. If you figure out where 135 is, it's in quadrant 2 with a reference angle of 45 degrees. So these two positions are both or each 45 degrees away from each other.